My name is Cesar Valles, and I am currently a senior consulting scientist at Chevron Technology Center in Richmond, California. I've been with Chevron for around 15 years in this area of petroleum chemistry. And before that, I worked for another 15 years for the PDVSA INTEVE, which is the Venezuelan research institution. It's really a pleasure for me to introduce Dr. Yunlong Zhang from ExxonMobil Research and Engineering Company. Yunlong is MIT to postdoctoral fellowship at MIT and a PhD in physical organic chemistry from Ohio State University. He is very interested in hydrocarbon chemistry, also we call it petroleum chemistry, structure, reactivity of heavy oil and asphaltenes, and carbon material. He really focused in the understanding of reaction mechanism. And recently, the last few years, he has amazed us with the work in non-contact atomic force microscope. This is a topic that today he's going to talk. Yunlong is one of the new stars in this field, and he has won several awards as mentioned in the screen. Without any further ado, it's my pleasure to present to you Yunlong. Yunlong, take it away.
Okay. Share screen. Can you see my screen now?
Yes.
Okay, great. Thank you very much, Cesar, for the kind of introduction. I don't think I deserve such a high compliment. So really appreciate. Before I start, I would like to thank Luis for organizing such a tremendous event for this monthly seminar series, and also for inviting me. I think I'm probably one of the first speakers from industry, so that's probably got me invited. So I really appreciate this opportunity. I hope in the future we have more people from industry to come to this forum, great forum, to talk about this. So hello everybody. I think it's really great to hear for this opportunity to give a talk to share our recent research about petroleum characterization using molecular imaging with the nc-AFM. So when I prepared this presentation, I have a couple of questions on my mind. For example, a lot of people will think this is very old stuff. Don't we know all the structures already? Why you are still studying them? And other people may ask, this is the fossil fuel. Why do we care about these structures? Hopefully in this talk, I will help to address some of these questions. For some of you curious, not familiar with ExxonMobil Research Engineering, this is our beautiful campus in Western New Jersey. This is not in Houston. You all may know our main campus in Houston. So most of the people of ExxonMobil Research Engineering is in this Western New Jersey, about 1 hour away from New York City. This is a historical site. We just recently celebrated the 50 years anniversary of this site's research here. So if you are nearby or around, please let me know. Hopefully after the pandemic is over. So let's get started. So petroleum have a very long history. So the earliest evidence of using petroleum is probably date to 5,000 BC. So this is a man-headed bull. Let me show my cursor here. The Sumerian god. People find the asphalt in the eye socket. Asphalt is used to glue the eyeballs to the eye socket. So that's what the asphalt means. Later on, I will talk about asphaltenes. That's from ancient Greek. Asphalt means firm, stable, secure, and prevent from falling. So that's what is today used as just like cement to glue things together. So, and over the long history, many uses has been found for petroleum. For example, adhesive, sealants, waterproofing. One of the most curious probably for medicine. Believe it or not, a lot of documents for the medicinal effect. So one of the most powerful use was the Greek fire. For some of you not familiar, you can Google and search it. That's one of the most powerful weapon in the Middle Ages. This is helped to defend the East Roman for many centuries. The formulation is regarded as top secret, so we don't know exactly what's the formulation, but historians speculated it is predominantly petroleum naphtha with pine resin and others, so water cannot be used to put out water. So petroleum at this long time is naturally occurring from oil sieves from ground or from rock. That's what petroleum means in Asia Greek. It means petro means rock, lium means oil. That's what we know as today. That's also in Chinese translated as rock oil. And so the modern history actually started in the mid 18th century. So the first drake well, this is in 1859 and spread out to the rest of the world. So the first use of petroleum is for illumination. So the kerosene lamp here is used. So the first use of the petroleum has been used to prevent the whales from extinction, because before that, whaling industry was one of the major industry. So for a long time, people hunted whales for whale oil for illumination. But shortly after a few decades, electrical lights coming out, and the new uses was found. So that's the Ford vehicle, the mass production. So since then, the oil petroleum industry picking up. So in addition to transportation, there's a lot of other uses. For example, electricity, petrochemicals, lubricants, and pavement, a lot of others. So today, the world oil production is really a huge number. If you're not familiar, this is you can find online. Today it's about 100 million barrels per day. The barrel is the older unit, the same as for wine container. And so a couple of months ago, Ripo gave a great talk, and he came up with this unit called a cubic mile of oil. So today our consumption is about 1.2 cubic miles per year. If you're still not familiar with how big is the cubic mile is, it's roughly everybody drink water or milk. So that's roughly everybody spending about half gallon per capita per day. So that's a huge amount. That's also going to, because most of them generating energy, that's how a big challenge is the climate and the CO2 emission. So this is oil, the global energy use evolved over time. You can see in the 19th century, from 1800 to 1900, the predominant source of the wood, even during the Industrial Revolution. So predominant source of energy was wood. And then you can see the first 50 years of 20th century was coal. And then starting in the 1950s, because of passenger vehicles, the oil and gas picking up, and also the nuclear, hydro, and other renewables coming to mix, we're going to expect more and more diverse of this oil, the sources of energy. So one of the biggest fundamental problem in petroleum is not as simple as you dig out the oil and that's what you need. So this is crude supply. You can see, and this is what we need: gasoline, jet fuel, diesel, heating, and a lot of time, what came out of the ground is not what we need. So that's why we need to refine them. A lot of time they are either boiling point too high or too many heteroatoms. So that's why we need to make cleaner fuels. So petroleum indeed has been studied for a long time. This is a part of my personal biased view about the milestones in petroleum characterization. So you can see that starting the 1800 to 1900. That's the main research is from in Europe, and the main method is repeated fractional distillation. For example, Michael Faraday distilled benzene, but he named it bicarbonate of hydrogen. That means C2H. It's not because he did experiments wrong, because the atomic unit, atomic weight of hydrogen was wrong by then. And then take about 40 years when Kepler came up with this very famous ring-like structure, and take another almost 90 years when Hugo figured out the aromaticity, explained why this is have 3 double bonds in the ring, but it does not have any property or reaction similar to olefins. So you can see we're not going to talk about all this chemistry and history. Just want to put the major petroleum characterization into this background. But now Benjamin Silliman is a professor in Yale. So he distilled kerosene and proved that this petroleum can be used for illumination. This is one of the major to prove that it can be used for illumination for petroleum. And about at the beginning of the 19th century, UV IR XRD has been used. You can see about 1930 or 40s, the trips found the porphyrins from petroleum. And you can notice that a lot of this work was using the very primitive tools of UV IR XRD. And a major event was GCMS around the turn of the mid-20th century. GC and mass spec came into play. That's really a very powerful technique. You can see this API project, American Petroleum Institute, petroleum. So that's between 1920s to 40s, distilled a lot of distilled and characterized petroleum compounds. Hundreds of compounds was characterized. You can see the column as huge as a person here. You can see that after GC was invented, a lot of compounds characterized much faster. About the 1980s, HPLC came into play. So more liquid compounds, higher boiling point can be characterized. So I put here at around 1960, NMR and ESR has very important, powerful tools here. So I put a Yang picture here because the famous structural asphaltenes. And around 1980s, Bolonzinski applied this liquid chromatography and proved that asphaltene is not a molecular weight of like millions, not a large molecule, but a smaller molecules. And then GC around 90s. One of the major milestones about 2000, FTICR came into to be a very powerful tool. A lot of compounds, molecular formulas can be characterized. That's a new term come into play called petroleomics. And then more recently, nc-AFM is used to calculate the structure. I'm going to talk about it. So this is just my personal biased view about this, the major events. So with these techniques and a lot of compounds that's been characterized, remarkable progress has been made. For example, in the 1930s, it's only about 100 compounds was characterized. Around 1950s, before the GC, that's only up to a few hundreds. And shortly after, you can see the API project 48, a few thousand has been characterized. That characterized today, really, it's hard to tell. So this is the petroleum world map made by Harold Smith around 1960s. So instead of tabulated all the compounds characterized, he made this map from this low boiling point to all the way to the very petroleum ocean high boiling point. You can see the capture. So this petroleum map captured the state of the understanding up to the 1960s. You can see most of the compounds that characterized is the lighter components. The heavier compounds is harder to characterize. So exactly how many molecules in petroleum? I would argue that this is still open question. So you can estimate in one droplet of oil, that's a total of 10 to the power 16 number of total molecules based on Avogadro number and average molecular weight of 500. And using the state-of-the-art FTICR, about today, we have 200 to 300,000 peaks can be identified, and each peak can be resolved into molecular formula. But from formula to molecular structure, still a long way to go, because for methane and ethane, you can figure out the structure just one isomer. But for larger and larger molecules, the isomers became exponentially larger. So this is just to give you an example here. A 40 carbon, just the alkane is estimated to have 60 trillion isomers. The same is true for aromatics, many structures. So how do we figure out the structure? One of the major techniques is called divide and conquer strategy. So this is analytical separation protocol developed by within our company, also my others also in the academic, has been developed and perfected over many decades. You can see many fractions that was fractionated and characterized. But still, the heavy molecules is a challenge because it's super complex. And over the many structures has been proposed. Here I classified physical models or chemical models. In physical models, that means these are based on physical principles, based on the assumption of like XRD, the lattice and rods, discs, and dots. For example, the Nallenstein paper model in before the World War II, and the Yang model in 1961, and many others. So this is it's very important to understand what each model means. Some of the model, like the Yang-Mullins model, incorporate both chemistry, structure, and physical properties. So a lot of the structure, chemical structure, have also been proposed. So this is a limited list of the structures. Please forgive me if I forget to include the others, especially I know many people in the audience have a lot of expertise. Forgive me if I forgot to include. So this is the structures. Some of the structures actually are wrong. For example, they could be radicals, but they didn't manage. Sometimes they could be olefin, but they don't mean olefin. So how do we know the average structure without knowing the individual ones? And also, how do we know any of these structures are true, and how do we know them? So this is a technique we've been working, coming into play. This is a visionary statement by Richard Feynman. He said if it's a strange substance, you just take a look and see where the atoms are. This is very straightforward from a physics approach. So this was unthinkable as a chemist. And this is just was recently realized. And I'm going to give this one slide overview of what is this, the history of this non-contact AFM. So first of all, it's a scanning probe technique. So when you have, based on the principle of tunneling current, when you have two conductive phases are close to each other. And the AFM is based on the frequency shifts. You can tell the topology of the molecules. And most of the time, it's based on silicon cantilever. And when the cantilever is very close to the sample, the cantilever will snap. So that's why most of the AFM is contact mode. It's touch the surface. So we're talking about a non-contact. So that's this is based on Franz Jessup, but in 20 years ago, we came up with a Q plus sensor using a quartz, made of quartz, the Q plus sensor. So this is very stiff, so that the tape is, even though it's hold very close, but does not contact directly. And lastly, Leo Gross at IBM found when you attach a CO molecule and the magic structure can be obtained. For example, this is the Penderson structure you can see, and some of you are very familiar. So you can see this is just like the ring structures. So a lot of work has been done. This technique is definitely not invented for petroleum research, and many papers, including a science paper last week, many many research has been done. But here I'm going to just focus about the application in petroleum, in characterizing petroleum structures. Before I go directly, I still want to talk about this technique is not very common. It's different than probably a lot of you are familiar with. So this is a picture of this instrument. So like this is the cryo stage. This is a instrument. First of all, it need to be very low temperature. Need to run a liquid helium. So 4.7 K, this need to freeze the thermal diffusion. At a 10 or 20 K, the molecules start to diffuse on the surface. So, and also need to ultra clean system. That means ultra high vacuum to have to get rid of all the contaminants. And most importantly, you also need to, the surface mostly is a single crystal copper 111, need to be atomically flat. Sometimes you need to prepare the mono layer of sodium chloride if you want to image the molecular orbitals. Also need to control the taper height, and because of the surface technique, the planar molecule is preferred. And lastly, you need to, how do you transfer the molecules on the cryo stage is open question, because you want to maintain this very low temperature, very high vacuum. So this is a lot of time it's a flash heating from a silicon wafer. So after all this is done, this you can collect this kind of image. You can see this little, this is SPM image. And then you can perform AFM to get individual structures. So the first work was done published even before, shortly after I joined the company. This is done by IBM with by Leo Gross, Bruno, and Leo with Oliver in JAX. And so in this paper, image the asphaltenes, compare coal asphaltenes and petroleum asphaltenes. So this is the coal-derived asphaltenes. You can see the ring structure is very clear. You can easily recognize them. And then this is petroleum asphaltenes. You can see this structure. There's only a few limited. This is although it take a lot of effort. Some of the rest of images very you can see it's very furry and it's not very clear. So we decided to do more work. This is that caused a lot of interest in the industry. And so that's how we decided to work together. And this is the paper published. We worked with, so IBM performed the work, and each of the 4 oil companies provide 2 samples to work. And that's with Cesar and Mike in the audience today, and also with Shell and Schlumberger. So this is a very rare study. I would say this is the only study I'm aware of. You see the big oil companies work together because they typically will trash each other and because they're competitors. So a lot of information, very valuable information here. So please feel free to make your own to study this paper. I think this is and so far this paper has been the most cited paper published on energy and fuels. So this is a really tremendous effort. This is done by obtaining the structures. It's take a lot of effort, but then what's next? So this is structure I tabulated in this book chapter. You can see a tremendous diversity. All this. So there are, we'll talk about several 2 areas of challenges. Firstly, it's experimental. For the petroleum structures, you can see from the previous image, a lot of moieties are not clear. For example, heteroatoms and aliphatic part. And also, how do we make sure this, the results is representative? So because there's such a diversity of molecules. So first, we compare this result with FTICR. And so you can see this is FTICR of the steam crack tar. We compare of the same sample. This is a acyl abundance plus. This is a Z class or aromaticity. This is the carbon number. And with the same sample AFM, we can collect this image or can derive the structure and get the formula and then map onto this abundance plot. You can see they are consistent, and then we can map all the molecules. So this is a show they almost overlap each other, obviously, because AFM can only collect a limited number of molecules. But I think this is consistent. You can see this is even on the most frequently observed molecules are consistent with the hotspots on the 2D plot. So we need to continue to work, even though this study is consistent, but we have been repeatedly to compare with AMR or with other techniques to make sure they're consistent. And also we need to figure out the architectures. So, and somehow you are familiar, there's a significant controversy or debates between the archipelago versus the island structure. So from an industry point of view, we don't care about this academic the controversy, but it's also important that this kind of structure, it's practical, because this structure will be convertible. You can convert this, chop off these weak linkages, and for this structure to be more useful. For this structure, it's hard to imagine it will be convertible under hydropresent conditions. So that's why this is important. And by working with Bruno and Leo at IBM, so we prepare this compounds to mimic this archipelago structure, and then we can image them. So this is the structures. This you can see. This is two different tip height. Here at a higher tip height and the lower tip height, you can see aromatic structures. This is pyrene, what we put down, you expect. And two, this is the carbons, this 10 carbon, 20 carbon, you can see individually. This is to show that this kind of architecture can be obtained under the same conditions. So this has been published. And also, as you remember, a lot of challenges. The petroleum structure is different with the coal and others because there's a lot of aliphatic components. They are very difficult to categorize. And in a series of studies, we prepare model compounds which incorporate different aliphatic linkers or naphthenic attached naphthenic rings and identify different conformations. So this conformation, for example, this arrow linkage have this two kind of image. So without knowing the structure, it will be very difficult to resolve the structure. And also for the methylene linkage, you can see there are 4 conformers we can identify. For 3 carbons, there are 8 conformers, becoming more and more complex. And this with 5 membrane ring, you can see there are 2 conformers. And with the 6 membrane ring, you can see there are this like flower or mushroom kind of structure. So this kind of study is important because we can compare with the unknown structure from petroleum, and then we can confirm their structures. So heteroatom is also very important. So this is a very well-known study from Aldo Topso. They are using the SPM technique to figure out this hydroprocessing catalyst. So recently we started work with Percy Zell at the Brookhaven National Lab to characterize this a series of model compounds. This is sulfur-containing compound. You can see this is sulfur atom in the middle. It's very easy to identify. But we also, through very careful imaging, realized that the sulfur, although it's very high, but the molecule is slightly tilted because sulfur have a higher binding affinity with the substrate. In this case, is a gold substrate, gold 111. And also nitrogen-containing compound is known as the catalyst poisons. So we need to figure out the presence of nitrogen and if they present or not in the unknown structure. So we figure out certain rules, the guiding principles to predict when there is a nitrogen in the unknown structure. For example, to modulate, to measure the frequency shift at each atom, we can characterize them. So another important problem is the metal containing compound. This also known as the poison, catalyst poisons. So in this work, we study the geochemistry problems. We study how these structures to understand the evolution of these structures. So this is the porphyrin, chlorine, and the various the EQ and DPEP porphyrins previously characterized from petroleum. So we isolated the purified petroporphyrins, studied with FDICR, mass spec, identify this 8 peaks, and then we use AFM to image the structure. And disappointingly, this this image does not readily give us this porphyrin structure. And we quickly realized that the vanadium have 2 conformations. One is this is the bright spot in the middle because the vanadium, the VO is pointing up. In another conformation is the VO is pointing down. So the O is the contact the substrate, so you can see the frame structures. But anyway, we still figure out that there are beta hydrogens that have a potential consequence from dealkylation during the catalysis pathways. So so far I described to you the challenges, especially from an experimental point of view, the metals, the heteroatoms, the aliphatic moieties, how do we confirm? That's also is a challenge from theoretical point of view. You have the structures, but so what? Are they different with what we predicted before? And is there any significance from the structures? So over the last few years, we have been working to categorizing this quantification of structures, identify the patterns, and think about what I found, and then to mapping against the also possible structures, and also understand their electronic structures. For example, everybody know that the pH is a lot of them are benzenoids. That means they composed of 6 membrane rings only. And what about 3, 4, 5, 7, 8 membrane rings? These are also possible in organic chemistry. We found that 5 membrane rings is predominant, especially 2 kind of 5 membrane rings. One is the 5 membrane rings with methylene unit in it. Another one is fully conjugated. It's called a nonalternant hydrocarbon. So what does it mean? What's the significance of this 5 membrane rings? And also even the 6 membrane ring, we can also, there are different condensation patterns. For example, we found the linear rings always make a turn after reaching 3. We call the rule of 3. This is because people know the Kinga structure is more stable. So that shows thermodynamic stability of these kind of structures. And also we can calculate the light properties, the light absorption, to understand why oil is black, certain structure absorbing the visible light. And in the past, there's a lot of study in this area as well. And also electronic structures to see the significance of 5 membrane rings. So the 5 membrane ring compared to 6 membrane rings, one of the consequences of the molecular orbital distribution. For 6 membrane rings or alternate hydrocarbons, the molecular orbital is symmetric, a HOMO and LOMO. But for nonalternant, they are asymmetric. That's created charge separations, typically have larger dipole moment. So that's one of the consequences. And also, we studied the aromaticity. Typically, from what I learned, that the pH structure, they are aromatic. They're, because of a conjugation, they are evenly distributed and aromaticity everywhere. But we can calculate a nuclear independent chemical shift. This is the TVPFT method to calculate AMR chemical shift. But you calculate the chemical shift at center of each ring as a measure of how much aromaticity is each ring. So from benzene, it's -10. That's very aromatic. And for cyclobutadiene is +18. As we know, it's anti-aromatic because this this double bonds does not like to conjugate each other. And then based on this, we can calculate. You can see that a 5-member ring in the center is close to non-aromatic. So based on this understanding, we can figure out that many of these structures. For example, you can see that this pH structure is composed of 3 units based on naphthalene benzenes. Although today I still don't know if this can be hydroprocessed, can be cracked at this location. But just to show that they realize that the pH does not be the same one big piece. There's the rules. Also we can understand the rules of the aromatic pathway. This is another paper published done together with Leo Gross science last year. For porphyrin, there are conjugated a total of 24 pi electrons, including carbon and nitrogen. That could be different pathways for a long time. Over half a century, people hypothesized that the aromatic pathway in porphyrin is very peculiar. It's called an 18-aniline pathway. This is the red highlighted here, but this two double bond here and these two nitrogen is just attached to them. And we use the EFM and see this is the structure, confirm this is the 18, that's indeed, these two corners are different apparently. And also, so all this is a very great, so it's important to understand what the images are. It's not just like using iPhone to take an image, take a picture, as you know. So important to understand what are this image? What is this bond stand for? And there's a lot of discussion in the literature already, and people want to understand to what extent the AFM image resemble a covalent bond. Recently, we studied this one, trying to understand the nature of the chemical bond. Chemical bond, is like a spring or glue to atoms together. We're trying to use the AFM to perturb the system, to break the bond. And you can see this is a porphyrin-like structure and the CO calated to it. And then we use the AFM tape to remove it and measure what's the force it takes to break this bond. It's measured about 20 piconewton, and then do the calculations to understand how the bond breaking process. So also typically when I talk to people around, people often think this is pH, just like benzene, all the bonds are equal, but in pH, a lot of bonds have slight differences and they have important consequence. So this is natural bond calculation. You can see that you can put ethane and ethylene as a single bond and double bond, and put benzene at a 1.44 double bond character here. And then a lot of pH have various degrees double bond characters. And now you can calculate the AFM structure. You can see many of the structure have high double bond characters. So this could be potentially the site for hydrogenation during hydroprocessing. And this could be also be used for reactions. For example, when under certain conditions, you can make the chemical reactions at this site because they have higher double bonds. Another thing, it's free radicals. It's also very popular, and I have recently got a lot of interest performed study. So this is based on a few radicals collected, imaged by AFM, and then rationalize there's different radical structures, and then to explain is how aggregation, the asphaltene aggregation based on the pancake bonding. And please just let you know that I didn't make up this pancake bonding. This is a new covalent bond character based on the radical interactions. So so far, I think I'm in the last 3 to 5 minutes. I want to share with you what does it matter by knowing the structure. A lot of time people think this is fossil fuel, and it doesn't matter because you put on fire, it doesn't matter. So I found this is very inspiring by a statement by Mendeleev about 100 years ago, that burning petroleum as a fuel would be like put money on the stove. So I think that with knowing the molecular structure, a lot of opportunities can be done. For example, making carbon materials. So in the next few slides, just to give you an example how we can, this is using this technique to figure out how the molecules are building larger to make useful materials. So in the past, the people have been trying to figure out from petroleum molecule, make it smaller, to chop it up to make a gasoline or diesel. And now we're trying to build it up from bigger to even bigger. So this is M50 page. Some of you are familiar. Very well-known material, have been studied extensively in the literature. And a lot of study has been done based on all kind of different techniques and based on characterization, based on AMR, elemental analysis, and mass bag, and the various average structure has been proposed. But we want to use AFM to figure out if any of this structure is correct and to what extent. And so next slide. This is the M50 pitch. This is the same material, and we characterize it. This is we recently built this technique with collaboration with the Princeton. And this is I'm the contact person from ExxonMobil steering this multi-million project with the help from IBM. And recently, this is the work image this structure M50. You can see a lot of structures has been imaged. And this is their structures. Some of the structures, for example, P16 and 17, this will be very hard to know their structures, but thankfully we have our model compound that we can compare. This arrow linkage, or you can see C3 linkage. That's how we can tell, confirm. Also, we can do molecular simulations based on the proposed structures and then confirm the image. So I would say, and then we can compare this technique with the AMR FPSR data to see what if the previous predictions. So in general, a lot of structures are pH structure with the methyl groups. So here, and sometimes have a 5-member rings. So we proposed how these structures are formed. And most importantly, this structure is known to form liquid crystalline state called a mesophase. And these molecules fuse together, become larger molecules like carbon fiber. And we try to understand how the molecules fuse together into bigger. How the first bond is formed between two molecules. And you can see this is a steel tube reactor. The molecule indeed become larger and still have metal groups, but less. And also we can do the reaction on surface. This is also very common, has been done, published many papers based on copper 111. While on the copper 111 surface, you heat the sample, obviously you cannot image at the same time, but afterwards, and then cooling down and image again, you can see the ginormous molecule was formed on the surface. And in general, you can see that the metal group disappears, they became a larger pH, but they didn't form a very nice graphene structure, and the 5-member ring is still there. So a hypothesis that the metal groups could potentially initiate the polymerization reaction. Things are still there, are still formed. So decide to design model compounds to study, because the challenge with this is, as the study material is all different, the products are also very different, and you don't tell what kind of structures form the product, because the reaction is not complete. That's certainly certain structures still reacting there. Okay, in the next 2-3 slides, I'll be finishing up because I see I'm running out of time. So this is the model compound we designed, dimethylpyrene. You can see under the same conditions, we form a black pitch material. With the pyrene itself, however, does not form a pitch material. You can see the color change, but over and over again, as a chemist, I know that you cannot tell by color because from GC, from other analysis, the products are even more pure than starting material, 99% pyrene. So please trust me, there's no reaction in this case. And you can also tell from TGA, for dimethylpyrene starting material, you can see they vaporized very easily under nitrogen. And on this page, you can see they are stable after even 500-600 degrees. So this is a show that they do polymerize. And then we studied using what happened. So this is based on the textbook and all the knowledge as I was aware. So generally people will predict the weakest bond will break, you generate a benzylic radical, and the benzylic radical attach to others. And what you form is the major product will be having this kind of structure with CH2 linker or form of family member rings. And under more severe conditions, you can form this kind of structures. So exactly what happened, we also using AMR, obviously. So we can see that compared to the reactant to product, the peak of broadening shows the methyl groups are change their position. But you can see that if they are a form of linked structure, you would expect to be in this region, but there's no peaks there. So what happened? We also do FTSCR, do other traditional technique, because the AFM is not a very convenient technique. It often take a long time, you can imagine. So we use the FTSCR. You can see 3 humps. You can see the monomer, dimer, trimers. So that show that indeed the molecular oligomerization indeed happens. Okay, so this is the AFM structure, just to show you. So you can see this is the model compound study, but many structures are formed. We can find studying material with dimethylpyrene, but we can also see the product, the coupled compounds and many compounds, even large PAHs. Next slide, I'm going to show you the structures. So here's the structure. You can see the monomers, the methyl groups, all changing their positions. They're almost completely randomized. And then dimers, you can see the most predominant structures are formed 6-member ring. So they didn't, it's very rarely they will have a methylene linker I would predict at the beginning. So, and even other structures, you can see trimers, even tetramers that wasn't predicted, wasn't detected by FTSCR also can be found. So what happened, what formed to this kind of structure? And then we can rationalize this, the mechanism. So this is earlier this year I have published. So indeed, that's confirmed the methyl group initiating the polymerization, but the mechanism is slightly different. So firstly, it's not cleaving of this bond directly because the literature have shown that this bond is pretty strong. It does not break until it's 800 or 1000 Celsius degrees. And so generally, people will believe you generate the benzylic radical, but why the benzylic radical does not form product and how the methyl group is transferred. And this is from a liquid field study. People generally believe that the methyl transfer is because of an apical attack by hydrogen atom. So the hydrogen attack the apical position and generate the methyl transfers. But exactly how the coupled reaction is formed, so we propose that is because the pi radical is formed and coupled with another structure generate this 6-member rings. And then we have to explain if every reaction is from H dot, so what happened to this guy? And it take a while to realize a lot of discussion with experts outside and internally, realize that the resonance structure also paradical. If this paradical react, then similar, this reaction will also, that's I can explain how the sigma rings form. Okay, so that's basically all I have for this. This is summarizing. So what do we have so far? Just to show that molecular imaging is a uniquely, have the unique advantage that you can image the structure directly without need the purification. It's a direct evidence of structures, and compared to a lot of others, will be very challenging. Although this is a very, very promising, we think in the future, a lot of challenges need to be addressed. For example, representativeness, how do we make sure the structure image that is representative, and also how make sure the structure is not a fragmented. Also, as I showed, nonplanar structures, the classification, understanding of the structures continue. That's a lot of directions. For example, I showed the reactivity is one promising directions, and building from large molecules to huge molecules, making coming materials. And we can explain the reactivities and also understand the geochemistry problems. So that's all I have today. I'm sorry for taking a little bit more time or a little bit too long. But before I finish, I really need to thank my collaborations. They did all this hard work, tremendous amount of work. First of all, by IBM in Zurich. So Leo Gross, Bruno Schuller, they have a tremendous contribution and taught me a lot from the very beginning. And also many others in the collaboration since for the heavy oil paper, working with a lot of other experts, Cesar, Mike Moore, and over the last few years and many others. I feel like I'm tremendously lucky to learn from them. And also more recently, we built this instrument by working with Professor Nan Yao and postdoc Peng Cheng, and established the capability, and also with the help for calculation from Professor Chalikowski, and also Brookhaven have some the heteroatom work really. So and also it's really important for acknowledge the help from the support from ExxonMobil that's allowed me to do this work and give this talk.